Alright, today we're going to be looking at Graham's law of diffusion of gases. We need to understand what rate means and what molecular mass means in order for us to understand what the Graham's law equation translates to. Alright, now rate and molecular mass. What does it mean to say rate? Rate is how fast a particular gas molecule is moving over a particular distance and time. So if we have two gas molecules, this big one here, let's say it has high molecular mass, and this small one here, let's say it has small molecular mass. When you say molecular mass, we mean the mass of a molecule. Alright, so this big one means it has high molecular mass, and this small one means it has small molecular mass. If they were to engage in a race battle, which of these two will get to the end of the race before the other? Let's see what plays out. Oh, wow. So the small one got to the end of the race before the big one. So what comes to your mind? If we're to engage a Ferrari and a truck in a race battle, which of the two will get to the end? Will finish the race before the other? Definitely it's going to be the Ferrari. Why? Because it's smaller. So because it's smaller, we tend to attribute being fast to it. And the truck, which is quite bigger and huge, will not be fast enough to beat the Ferrari, right? Great. So we can relate rate and molecular mass as inversely proportional, meaning that if the molecular mass is high, the rate, how fast it is going to be quite slower, right? Great. So we can say the rate of diffusion of gas is the amount or the volume of the gas that traveled per time in a specific distance. How much of that particular gas traveled in a given period of time. All right, great. So we can say that the rate is equals to the volume over time. How much of the gas and what amount of time did it take that volume of gas to travel? So let us look at this example. 50 centimeter cube of a gas traveled over a specific distance for 10 seconds. So since we know that rate is equals to volume over time, so we can go on and say that rate equals to volume over time. Since volume is equals to 50 centimeter cube and time is 10 seconds, so we can say that rate equals to 50 over 10, and so rate equals to 5 centimeter cube per seconds. Very simple. So I want you to try this out. 90 centimeter cube of a gas diffused through a porous spot in 15 seconds. So what is the rate of the gas? Okay, I assume you're done with it now. So rate is equals to volume over time again. And then we know that the volume is what? 90 centimeter cube. The time is what? 15 seconds. Very good. So that's going to be rate equals to 90 over 15 to give us 6 centimeter cube per second. That means in 1 second, 6 centimeter cube of the gas travel. Right. That's how fast the reaction is. So the Graham's law of diffusion of gases now states that at constant temperature and pressure, the rate of diffusion of gas is inversely proportional to the square root of a density. Now I want you to take note of this inverse proportionality. It simply means that if something is going up, then the other side should be going down. So if the rate of the gas is increased, definitely the density should be decreased. All right, very good. So now if the rate is small, definitely the molecular mass or the density should be big. All right, very good. So this is the formula. The rate is inversely proportional to the square root of the density. So the density here also translates to the molecular mass. So we can equate density to also mean molecular mass. Very good. So when the particular gas is heavy, it tends to be slower, and when it is light, it tends to be faster. Good. So for two gases, when we have two gases, we can then change the formula to mean R1 over R2 equals to square root of M2 over M1. Now remember I mentioned that we can say molecular mass is still the same thing as the density, okay? Very good. And since this is the rate of the gas 1, the first gas, then this is the molecular mass, the square root of the molecular mass of gas 1. So they are inversely related. So it's still the same thing. Alright? Good. So R1 is the rate of gas 1, R2 is the rate of gas 2, then M1 is the molecular mass or density of gas 1, M2 is the molecular mass or density of gas 2. So when we are talking about density, we just change this M2 to P or the rho sign like this, alright? Very good. So let us look at this example. If 300 centimeter cube of oxygen is diffused through a porous spot in 50 seconds, so this is the volume, this is the time, and please take note that we are working with oxygen, the first gas. How long, that's the time, how long will it take 500 centimeter cube of hydrogen, this is V, volume, of hydrogen, that's the second gas, so we're working with two gases now, to diffuse through the porous spot. So we have H equals to 1, O equals to 16. Very good. So let us work with this formula here. Rate of O2 over rate of hydrogen. Then we have the square root of the molecular masses of the gases. So we work with rate equals to volume over time again. So rate is going to be what? 300 centimeter cube over 50 seconds for the rate for oxygen. That's going to give us 6 centimeter cube per second. All right, what about the rate for hydrogen? That's going to be 500 upon T. You know, we don't have the time yet. We're looking for the time. So that's going to be T. So 500 over T. Very good. Now, what about the molecular mass of H2? Now, you should notice here that H equals to 1. This is the atomic mass of hydrogen. But hydrogen exists as a diatomic molecule, H2. So if H is 1, then H2 is going to be what? 2. Very good. So that is why we have 1 times 2 equals to 2 here. All right. So now the next one, the other gas is oxygen. That's going to be MO2. That's going to be 16 times 2 because oxygen also is diatomic, O2. And we have that O equals to 16, so O2 is going to be what? 32. Very good. So if we substitute all these answers into this equation here, we are going to have exactly this. So this is 6 translating to RO2, then this is 500 over T translating to the rate of H2, and then this is the molecular mass of hydrogen, the molecular mass of oxygen. So if we go on, then we can just put these two over 32 under the same square root, all right? All right, so we can just do the mathematics and change this fraction into this, all right? And then when we divide this by this, we have 1 over 16. Very good. So we can then move on to find the square root of 1, which is going to give us 1, and square root of 16 to give us 4. So then we cross multiply 500 times 1 and 60 times 4, which is going to give us 24t equals to 500. So then we can go on to divide both sides by 24 to give us t equals to 500 upon 24. And that's going to be what? T equals to 20.8 seconds. And we are done. So it's quite very simple.